Yeah, so then now the recording's on. Now, yeah, now you can start, Tom.
Okay, thank you. Okay, away with the window, or make it a side window of some kind. Okay, welcome everybody to the third session of the Software Engineering Architecture Ideas presentation, which I also call the Systems Engineering Architecture. And here is the C, S-E, ha ha ha, but very nice C picture there. For those who are just joining us, the book, which I'm using as slides and which this is all based on, you can either scan the QR right now with your phone, or you can use take a photograph of the screen and use this link, tiny URL, syst and arc book, and you can share the book with anybody, and you can steal all the ideas and get rich. Here's our outline. We started with an introductory day, and last Thursday we did number 1, value-driven architecture, and today we're going to do the third one, so it must be architecture efficiency, chapter 2, and then Thursday we'll do constraint respect architecture. And here's just passing some of the things we've done, all about stakeholders and that kind of things, and value, the idea of value and costs and resources. And we took a look at an impact estimation table where our different architecture alternatives, which are these columns here, we are evaluating the costs, very different kinds of costs. And we're even computing the value to cost ratio, subject we're going to go in more deeply today, finding this architecture to be in green the highest value to cost ratio. Okay, so this is just reviewing. We are going to look at, I think we're going to pick up here, even though I should have done it last time, constraints, ideas. So let's start with one idea that one constraint on the architecture choices is obviously how much time we have to implement it. If we have to deliver in 1 week, but our architecture would take 1 year, we can't choose the architecture. Same if the architecture costs $1 billion and we only have $1 million, we cannot choose the architecture. So clearly money and time are variable constraints or resource constraints. And there are any kind of limited resource, which is what we're dealing with here. We can state what the limit is, and we can see to what degree the different architecture options or complementary architectures steal those resources. And at some point they steal so much, we get a signal saying, you cannot do all these 5 architectures. They would take more than is allowed of the resources that we have allocated. Of course, you can negotiate for reallocation of resources, bigger budget, longer deadline, and maybe squeeze your architecture in there. But my main point is that the architect must seriously consider multiple types of resources. And there are many architecture practices that don't even seem to look at the resources at all, let alone during the detailed choice of single architecture or sub-architecture ideas. And but for me, it's an absolute necessity that we look at the resources immediately, and we throw away very quickly those resources that those architectures that cost far too much resource, or renegotiate the resources. Here is the general idea of constraints. So we were looking at what I call variable constraints, that is more or less money, more or less time, more or less people. But we also have binary constraints as a type. And binary constraints are, as the name indicates, black and white. You either, this constraint either applies or it doesn't. You meet the constraint, you don't violate it, or you do. So a simple example was all the architecture must be from Norwegian suppliers. Okay, so there are either the suppliers of the architecture are Norwegian or they are not. Another example of binary constraint would be that the architecture does not violate any European law or doesn't violate any European privacy law like GDPR. Okay, so two types of constraints, binary. The point is we need to state what the constraints are, make them visible, and then every time we are evaluating any architectural idea, somebody needs to ask the question, does this violate any of the constraints, either the scalar constraints, money, time, people, or the binary constraints, legal, not legal, that kind of thing. So that's what so here are some diagrams about scalar and binary constraints. I don't think you can look at them if you like, but it's just going into more detail about two fairly simple concepts. Now, here's another kind of thing that could be considered a constraint. They are what I call side effects. So let's say we have what I call our top 10 objectives. And let's say, to keep it simple and illustrate it, that these objectives are major qualities like security, usability, flexibility, availability, reliability, and things like that. So let's say we are trying to architect the security objective, and we pull in some security ideas. Now, it's very many practices and everyday practices, they do what I call one-to-one thinking. I need security, therefore I'll have an architecture called encryption. And they're all done. Now, the danger there is that that might be true, that encryption will help your architecture, but that encryption will begin to hit some other constraints. For example, it may cost some money. It may cost some time resources to translate in the system. And it may even threaten other major top 10 objectives, typically usability. Every time you tighten security, you tend to reduce some kind of usability a little bit. And so that's my main theme here, that the good architect has to examine the side effects on the other objectives or requirements, same thing for the moment, or stakeholder values. You can't just say, it's good, encryption is good for security, therefore we'll do it. You have to say, does it help or hurt any other side effects? Does it help or hurt, for example, the usability, the reliability, and these things? So, so this is the main point I'm trying to make here, is that we need to get away from one-to-one thinking, which is very human. It's almost a desire to simplify. I'm thinking about security, therefore I'm going to think about certain architecture ideas for security. But we have to ask, these architecture ideas for security, do they help or hurt any other major values? Some of them could wipe out other values. They could make it impossible to attain the user friendliness, which is also a minimum critical requirement for the system. So we have to somehow look at them. So here's the question: what are the side effects of our architecture on all the other critical stakeholder requirements? Okay, and before that, we even have to ask can we afford the security architecture? Is it within budget, within deadline, within the warm bodies we need to make the system? So, these are side effects on the resources, and then we have side effects on the values, two different things. And to do this, we need a method or a tool. So I'm going to introduce, I did introduce already the impact estimation table to look at the this thing here, the side effects of any architectural component on the money, time, people, and other limited resources. But now I'm going to take a look at the top half of that impact estimation table. And in the top half, we have the a set of value requirements, okay? And this is these examples here are actually taken from an analysis of the United Nations sustainability goals, the one where all the Norwegian ministers have a little badge on them saying we in Norway subscribe to the sustainability goals. And I have a little book for those who are very interested in this called Sustainability Planning. And I assume you will find that in the references at the back of the C book, where I analyze those goals and try to quantify them. So this is from that example. So end poverty is actually one of the top 10 goals. And so let's just say we stated the goal. We want 100% ending of poverty here. And then we have various strategies. So we have a main strategy one for ending poverty, which not surprisingly is rated as satisfying our goal 95%. We're almost there with some ideas, which are, this is just what I call the tag. So you'd have to go to the tag for the bright idea, the strategy, the architecture, the sub-architecture, and find out exactly what it contains. But when you do that, you can estimate how good it is. We'll get into the how do you estimate and things like that later. But somebody has estimated and says, well, it satisfies our goal of getting to 100% reduction of poverty at a certain time or date, like 2035 or something like that. And it gets us 95% of the way. So pretty good architecture, but not enough. This little white area says, we don't even believe that our architecture for ending poverty is good enough to actually get to our goal on time. Now, since we're solving the problem of all the United Nations goals at the same time, we have a strategy for ending hunger, which is one of the goals, this one. And we have a strategy for healthy lives, which is this goal, etc. So for every major goal, we have a set of strategies for dealing with them. And this set of strategies here is our total architecture for attaining our set of United Nations goals, maybe for Norway, for example. Now, in this table, before we make an estimate, we have a little starting point, which is question mark, question mark, question mark. And that means nobody has evaluated how well the end hunger strategies or architecture will help us end poverty. With a little bit of luck, maybe some of these strategies will tackle that last 5%, and we will, with the help of some end hunger strategies, actually achieve the end poverty goal fully. But nobody knows. You've all heard the term known unknowns. So here is a tool, an impact estimation table, which, as you can see, you can do on any spreadsheet. And it allows us to see that we have a known unknown. That is, we do not know how much our sub-strategies for ending hunger influence poverty. With a little bit of luck, they would go in positive direction and we'd achieve them. But for all we know, they could be negative or strongly negative. And in a sense, we earn 95% with this architecture, but we lose maybe 50% with this architecture and 30% with this. A lot of negative side effects, these are called. And because of the existence of these other strategies, we're just simply not going to reach our goal. So the unknown, in other words, implies that we can have, with a bit of luck, positive effects. Here we can see the end hunger goal has 96% effect on the end hunger objective, but let's see, the end poverty strategies also have a 42% effect on end hunger. And with a little bit of luck, these two combine somehow, and the two of them get us to the goal of end hunger. How they combine and whether they combine or not is a subject to be discussed later. But the important thing on this table is there are some evaluations done usually using evidence, facts, and things like that, which we document. So it's kind of a scientific or engineering method here. But if at the moment we have our starting point where nobody's estimated anything, we have a known unknown, and it can be severely negative and very destructive to architecture. Here, somebody has taken the end poverty strategy and taken a look how it impacts healthy lives, United Nations goal, and concluded that it's minus 42%, which is a severe hit. Okay, especially as the healthy lives thing isn't even evaluated with how that's, and we have a little 23% help from the end hunger. So basically, we're losing here. We don't have enough positive architecture to deliver healthy lives. Okay, beginning to get a feeling for how this impact estimation table works. It forces us to evaluate the side effects. So once you're staring primarily at poverty goal or objective or requirement, everything else here becomes, by comparison, the side effects. And these costs are another form of side effects, but these are side effects on values, and these are, if you like, side effects on costs, okay? And my point is, you can't just look at any one of these architectures and say, isn't that great, 95%, we're all done. You really have to, as in the kind of architect I'm trying to train here, you have to evaluate the side effects on all your other critical goals. These are critical goals, meaning if you fail in any one, your entire project has failed. Okay, so it's like body components. It's all if you fail in your brain, your body's dead. If you don't fail in your brain, but you fail in your heart, your body's still dead. These are all critical medical factors. So think about these as components of a body where if any one of them is not good enough, your entire system is dead. This is why we call it system engineering architecture, because we are forcing ourselves to look at the whole system, all of the architecture, all of the objectives, multidimensional objectives, and all of the costs. Okay, so if you learn one thing today, the idea that there is such a thing as a table, an impact estimation table. Here's the word impact estimation table. And it enables us to look at all of our architecture as we accumulate our ideas. It enables us to look at all of our critical objectives, the values of the critical stakeholders. And a lot of architecture methods talk about values of customers, but if you ask simple questions like where have they stated these requirements and have they quantified them, so we can do quantitative analysis of our architecture, the answer is you won't find it. So this is the most important single thing to add to any architectural method or architectural tool, is being numerically explicit. Exactly what are these critical values? And you have to do that numerically, a subject we're going to return to many times here, but this is the key cornerstone idea. And of course, you need to, we all know that you need to quantify your budget and your deadline and other resources, but not everybody understands that you can and must quantify all of your qualities or values. They don't know how to do it, or they say it's soft and it can't be done. That's called ignorance, but we'll try to do something about that ignorance if you happen to have it, okay? You must quantify your values so that you can quantify the contribution that your architecture makes, and that's done here in the table. We have a way of, an oversimplified way, admittedly, we can add up all the percentage contribution, and we get a number, in this case, 128. And for the next architecture, the end hunger architecture, we add up, we get 140. So we can see that overall, algebraically, if these things add up, which they don't really, but we're making a simplified assumption, a simplified model, 140 is slightly better than 128. The lack of exactness of the estimates and the model mean that there's no really significant difference between these two. It's a toss-up. But here, there's no toss-up here. Nobody's evaluated anything about the third architecture. It's a complete unknown. And if I have to act like find an early agile delivery sprint, then I would choose one of these two. On balance, maybe this one, which is 140. However, if I wanted in the short term to deliver results in end poverty, I'd probably choose the end poverty strategy, just because that's more powerful right here. And I want maybe some short-term results there. In other words, what I'm telling you here is we can use this table to decompose our overall architecture. This is number 1, number 2, number 3, number 4, and choose one of them to start delivering early. So let's call this Agile Architecture. Agile meaning step-by-step delivery. And so one potential early step is end poverty. And because the other ones have unknowns, and the end hunger doesn't do a lot for poverty. So if I prioritize delivering end poverty early, I would choose the end poverty strategy, which not surprisingly does a good job because it's designed to do. It's chosen architecturally. If on the other hand, somebody said, no, I want to end hunger first, then I would choose the end hunger strategy because it does a lot here and it even does a little bit here. That's pretty good choice. Okay, so on to today's major subject. I've got a half an hour left, architecture efficiency. And we've got some basic ideas. So efficiency means that the architecture has a very good set of values it can deliver at very low costs. So effectiveness is just the values, okay? But the moment you use that word efficiency properly, some people use it improperly and mix it up with the word effectiveness. Another good English way of saying it is cost effectiveness is what I'm talking about. The word cost comes in. Kostnadseffektivitet in Norwegian would be what I'm talking about here. So we have some concepts here. So this is a way of thinking about the profitability of the architecture, okay? And I haven't heard that term too much in the architectural methods I've looked at, you know, how profitable is any component of the architecture and the total architecture. So obviously in profit-making corporations, doing architecture profitability would seem to be the right thing to do. But even in government projects, we're talking about profitability means giving the highest set of values to the taxpayers and government at the lowest possible cost to the taxpayers or government. And we're definitely supposed to do that, but probably shouldn't call it profitability. Doesn't sound like a government thing, okay? But government cost effectiveness does sound like a good thing. So the question, I think everybody would agree, in principle, we should be cost effective in our architecture, but how do you do it? And that's what I'm teaching, exactly the tools for doing it. Because what I find is the other architectural methods even talk about it to a degree. They talk about values, but again, when you look, do they have actual tools to make these numeric and visible and clear? The answer is they do not at all, ever. Any of them. Show me tools that do. I can't name any, and I've been studying the field for quite a long time. Okay, now here's another concept, the idea of, do you have a good architecture? Okay, and so one way of defining good is to say it's cost effective, and say by the word good. Now you could by good just saying it's effective, it delivers all the values, and you don't think about cost. And you could even declare good to mean really cheap and really fast. Okay, but I think it's normally necessary to look at both parts of the equation, the values and the costs. So I'm going to say good architecture is referring to something that gives good values, and not just good values generally, but good values in relation to the requirements and objectives we've set. So this is very tailor-made. Good architecture is not a general thing. It is specific to your project and to your project requirements and your project limited resources and your other project constraints. For example, if you violated a binary constraint by violating the GDPR privacy laws in Smittestop, for example, then it would not be a good architecture for similar to use. Okay, so good has to encompass not only cost effectiveness, but not violating any other specified binary constraint. And I should probably put that in there and edit the book there, but we'll leave it there. Okay. Now, how skilled is an architect? Okay. And I'd say if we had an architectural competition, which is actually the normal thing in building architecture, to have competitions for building, I would say that the architect that gave the highest values, plural, for costs, plural, would be, I would say that was the most skilled architect or architectural group. So now we have a numeric definition. In fact, even a way of winning a competition would be the one that gave the, within the constraints, the highest level of values. There's a concept there of meeting some minimum levels and meeting some targeted levels. We'll get back to that later. But assuming you've met all the minimum constraints, simply the one that delivers the most value for money is even a way I've heard government ministers talk about quite happily. Okay, so in other words, architectural efficiency, that's what the AE stands for here, is a way of comparing architectures and selecting alternatives. Okay, so now we have a tool for making decisions that can be declared in advance. And so we have a more objective way of choosing things and choosing winner architectures and winning architects and stuff like that. Now, it turns out the architectural efficiency is also a way of prioritizing sub-architectures. So we're not going to build all sub-architectures simultaneously and then, deliver the whole system, big bang. We are agile. Every large project should be done in an agile way, and everything I'm teaching is very agile. And so we need a way of prioritizing sub-architectures. In other words, which sub-architectures are we going to deliver first? And that means we're usually going to install and integrate a sub-architecture, usually in an old system to begin with, like the existing social security system, the existing national health system. And we're going to see if it works and what it really costs. At some point after we have delivered all planned sub-architectures and achieved all values and not used up all of our budgets and time to deadline, then we will be done. And we will have the new system, and the old system will have at least partially disappeared, maybe wholly disappeared. And that may be an 8-year process for something like a Axon one patient, one journal project, which is proposed in Norway. And it's proposed to have it might be 8 years, but every year, 1/8 or more of the value should be delivered, and at no more than 1/8 of the cost of the system. And we'd have a form, and maybe in 1 year, we would attempt to deliver, say, monthly increments. So 12 times a year, we deliver some form of sub-architecture. We'd validate the sub-architecture. This is exactly the same as scientific method. We have a hypothesis. If I use this sub-architecture, I'll get so and so much security. So we install it, and we measure how much security we get, and our hypothesis about security using the sub-architecture will be validated or invalidated. Okay, so we're talking not only of Agile, but we're talking of literally of core scientific method. And wouldn't it be nice if architecture used scientific method as its way of exploring architecture and validating architecture? Now another thing about architectural efficiency is because in the word efficiency is the concept of cost, is that we're forced to do resource evaluation. The current method of resource evaluation seems to be the architect makes an estimate. So we take PwC's estimate for Axon project in Norway, and I think it was 22 billion kroner. Okay. If I'd ask everybody here, how many billions of kroner do you think they really would use at the end? I don't think anybody would imagine they really just use 22 billion kroner. What about 3 times that? 66 billion kroner is a good first estimate of what IT projects really cost. But are we willing to spend 22 billion kroner and say, oh dear, the Axon project is only 1/3 finished? And then the government's in a bind there. They've already sunk their 22 billion. So they're thinking, if I don't give some more money, I won't get anything for my 22 billion. It'll be totally wasted. So they're conned into continuing funding the project. I don't think projects should be funded that way at all. I don't think there's any harm having a long-term estimate or prediction like 22 billion, and 8 years. But I do believe we should prove the cost and the timing incrementally in agile steps. Okay, if we say it's going to take a month, hopefully it won't take more than a month. If we say certain things will take a year, hopefully it won't take more than a year. If we say it's only going to take 1 billion kroner, which is a lot of money, hopefully it won't take more than 1 billion. And if it does take much more, we will learn early that our architecture costs too much money or time, or is not valuable enough. And that is in time to do a very dramatic thing I'm going to be teaching here, which I call design to cost architecture, or dynamic design to cost architecture, if you're doing it in an agile way, step by step. So the architect has the power of choosing architecture which is cheaper and faster. And I think that's the main way we need to get control of long-term costs, is we put the architect on the spot and say, your job is to choose architecture which uses the least amount of time, the least amount of people, the least amount of money. And your job is to validate at early stages that it really does take the least amount of time and the least amount of money. And if not, either you or somebody who replaces you will get in there and find something which is cheaper. This is a well-known engineering method. Look it up. Google design to cost. And we know how powerful it is within IT, looking at the IBM clean room method, because these clean room projects, which were done on American military and space projects at IBM, were always delivered on time and under budget, but they were at state of the art. And it's because they did dynamic design to cost with the architect in control. So I write about that quite often in my books and papers, and we'll no doubt get to it sooner or later. But look up clean room in my writings to get the detail there. So I'm talking about a whole different way of costing and controlling the costs of our architecture and our IT systems. One, we have to implement the cost-bearing architectures in small steps. We have to measure what they really cost compared to the hypothesis. If we have very negative results, we have to change the architecture. And in general, there's always a cheaper architecture out there if a smart enough architect looks for it in a serious way. Lazy architects just grab the first thing they think about. And I've seen this in all the architecture methods I've been looking at. They're not asked, what will it cost? They're not responsible for making sure it doesn't cost more than that. And this is the reason our projects cost ridiculously much, run over budget, because the architect is not put in control of the resources and costs. And I think that's professionally unacceptable. Okay, so this concept here of architectural efficiency forces the architect to be in the loop of figuring out what we, can do. Now, let's see, I need to, well, let's see. Okay, we're here. Trying to figure out why I'm not getting the last half of the page there, but all right, let's not worry about it too much. Okay, so let's see, I'm gonna skip that one. Another thing we do with the architectural efficiency is, and it's intentionally invisible up in the table here, but later we'll get into the idea that when making an estimate, we need to estimate the riskiness of the architecture. In other words, the first thing I do is say, okay, you have said 42% is the impact of the architecture, but could it be less or more, or is it exactly 42%? And usually people will admit, well, it could be less and it could be more. I said, well, give me a number. I mean, plus minus 1%. You've said it's not plus minus 0%, plus minus 10%, plus minus 40%. Give me a number for effectively the range that experience says it could be. In other words, how bad could it be? How good could it be? And we literally write down that number in a corner of the table called the plus minus uncertainty. And we're forcing the architect to understand the architecture so well that they understand the range. For example, if all experiences, it's sometimes down there and sometimes up there, then it's plus minus 30%. And that means, although we're guessing at 42%, don't be surprised if it isn't 42 minus 30, only 12. Okay, so this is one element of risk evaluation by the architect built into the impact estimation table. We'll get back to that later. We have a separate chapter on risk. The other thing we do regarding risk, and I'll tell you right away, but we're going to look at it in the risk chapter, is we say, what are the facts that told you that sometimes only 12 is delivered and sometimes 62 is delivered? Where are they? Was it a project we have done earlier in the government of Norway? Is it a project done in Northern Macedonia for the Axon system? Where do you get your facts? What is the source? And if you know the source and you go to the source, you can usually decide whether the source is credible or not. Okay, so if the source is just some guy I met in a bar when we were drunk, that isn't a very good source and it doesn't have very high credibility. If it's several written reports by different governments in small countries like Macedonia and Norway that said the Axon project should not cost more than $1 million, which is, by the way, I'm not making that up, it's true, take a look, then that has a fairly high credibility of what the cost could be, something like $1 million. And then so the cost idea of 22 billion is absolutely ridiculous, using fairly credible information about what Axon-like systems have in fact cost in small European countries like ours, in this case, Northern Macedonia. So those are two examples of what we're going to do with risk. Right now, we're not dealing with risk as much as we're dealing with side effects and costs Okay. However, we can use those numbers of the plus minus uncertainty, and we have a number for the credibility where 0 means no credibility and 1.0 means perfect credibility. We're actually going to use those numbers to compute new value, let's call it pessimistic values and pessimistic costs. So pessimistic value, if you have 42 plus or minus 30, is 12. Okay, that's like worst case. So the architect can analyze the worst case for a whole series of things and offer to management that, well, if everything went badly, we could end up with the following result. And do you accept that? Shall we move on? Or would you like us to find architecture which doesn't have those bad worst case uncertainties? In other words, change the architecture. Anyway, that's risk quantification. Okay. Balance tool. I think architecture is all about balance. In other words, having enough values to be very satisfactory at reasonably low costs within your budgets and deadlines. And I call that balance. So it's not about extremes, finding the perfect values at 0 cost. That would be extremes, and we're not looking for balance. Okay. And finally, the information from architecture efficiency, including the risk information, can be used to decide pretty good sequencing. It doesn't have to be perfect, but if the smartest thing in the world is done in 8 years' time, according to the PwC plan, that's not very good sequencing. Maybe it should be done in the first year, is what I'm talking about. So I've tried to show this idea graphically. Here are all the values, and here, all the costs, excuse me. And here are all the values, and I'm trying to get as an architect, I'm trying to find a reasonable balance. I'm also taking into consideration the risks and uncertainties. That is, I'm modifying these numbers with my risk information to get a balanced architectural efficiency with regard to risk. Okay. Now, if I had to stop there, I'd be dead pleased with today, giving you a lot to think about. But I do have a little bit more time before we go to questions and answers. And I'd encourage you to think of some questions. We sort of ran out of questions a little bit too early for my taste. So if you start thinking about questions, we'll have a whole half hour allocated, 5 o'clock to 5:30 Norwegian time. Okay. Just before the coronavirus struck in March, we were holding an OSWA live course at guest was IBM, and we all knew there was talk about closing down the Holmenkollen skiing event in 3 or 4 days in the weekend. So we had fun guessing, would they close it down or not? They finally did close it down. So we knew Corona was coming, and we had the 2-day workshop, which I'm love to get back to holding, even if we have to find a way of doing it over the net. I'm going to be doing this workshop with one of my clients in the coming weeks. We've already decided to do it. So I guess it can be done. But one thing I do is I ask the class, what would you like to choose to work on as a project? And we quickly agreed something about planning to save Norway from the coronavirus would be nice. So that's what we're doing. Here are the requirements we came up with, and here are the costs we came up with, and here are some of the architectures we came up with. Basically, in small teams, people pick one stakeholder, could be the Department of Health, and then I asked them to find just one value or requirement that's dominant or critical for them. Let's just say it was get people where they need to be, okay? And then I asked them to find one architecture component, let's just say transport architecture, which will get us there. I guessed on that because it had the most here. And then we end the second day by building this table, which they did, and we get an overview of, within 2 days, we get an overview of what are the quantified objectives. These can be reviewed by the managers, for example, the leaders in the government and community. And then the architectures they're thinking of can be looked at. For example, maybe we chose an architecture that violates some Norwegian law without being aware of it. And they would say, well, very nice, but did you realize this violates the Norwegian law, that we're going to follow the European laws, that we're going to have the GDPR privacy? Oh gosh, we forgot that, said Simula. We'll change the architecture. And then it evaluates the contribution that this architecture makes to all of the goals, and then it comes up with, in the case this fact, the transport architecture was the architectural winner. That is, the value to cost ratio of that was 40, and the others are down at a mere 12 or 39, which isn't that much difference if you think about it. And it turns out when we took risk into account, the winner was the Ture's team's architecture, called Ture architecture there. So in other words, an architecture that wins without regard to risk with optimistic thinking might not be the same as an architecture that wins with regard to risk thinking. And that's why we need to take the risk thinking in. We will choose different architectures, or different architectures to begin with evolutionarily or in an agile way. It even turns out that the third architecture won when we did what we call the worst case, which is considering the plus minus uncertainty of the architectures and the credibility at the same time. So extreme risk analysis gave yet a third different architecture. So this is what really happened on the last time we held a course, OSWA course in Oslo. So maybe we'll figure out a way to hold that. They're a lot of fun because I don't lecture very much. We just do it. The table is there here managing 6 different attributes, 4 different solutions, and 2 kinds of risks and things like that. Okay. So, but this can be done and on any spreadsheet, although we happen to be using our little tool, Valplan, which anybody can take a peek at too. Now, what you can do with any spreadsheet, of course, these spreadsheets can be, even a simple one can be kind of overwhelming because there are, so many factors to look at. Typically, a spreadsheet is actually 10 by 10, and there are 100 little intervals to look at. So that's quite overwhelming in a management presentation. So when we're going to simplify for management, we just say produce bar charts from it. So here we have the different architectures. Here's the transport architecture. And here we have the sum of 4 values. So this is the overall or total impact on our critical value requirements. So we have 3 pretty good architectures, 1 weak there. And then these are the different cost aspects. So we can say that from a value to cost point of view, this gives so little value that one of these other ones surely has to be it. And even just visually, you can see that it really doesn't matter which one of these you choose, because they all give very high sum of values at very low costs. And that's good enough to say, I'll ask a manager which one is his favorite one, and we'll do that in the coming month or year or something like that. So this is a simple way of analyzing and presenting architectures, and maybe the reasoning why we're saying, forget this for the moment, even though your favorite chief executive officer chose it. And any one of these will do. So we as architects don't care which one you choose. So you can have a little discussion. Just tell us to do the transport architecture first. Okay. So, so here we are looking at all kinds of, now this is actually part 3. So actually we've done part 2. We only have 6 minutes more left. So I think what I'll do is I'll quickly review it, and then we can go to question and answer time. So let's see. Okay, the first point I made was about side effects, that in any architectural situation, we need to acknowledge that in the architecture requirements, the input to the architects, which we're very bad at doing methods-wise now, almost everywhere. I mean, like absent or ridiculously weak is what I'd call all of them. We have a set of the most critical objectives, okay? There are other objectives outside of these which are less critical. We acknowledge them, but we're going to prioritize the top 10 and work on them until they are cracked. And then we have energy to look at number 11 to 20, the second top 10. So it's not that there are only 10, but we take a limited quantity of the critical things, and we're dead happy if we can do something with them, especially in the short term. And my major message here was that any given architecture or architecture sub-architecture idea needs to be evaluated not only on how good it is for its major purpose, poverty for poverty, but what happens when we implement it to the other critical goals. Oh, nice effect here. Oh dear, very bad side effect. Nothing particularly good or bad here. Oh dear, we don't even know. It could be a massive bad side effect which disqualifies us, but we don't even know. Okay, here we don't have the question marks. It means we think the effect is 0. That is, there is no effect, which is quite different from unknown, which could be a very massive side effect. Okay, so my major point there was we have to, like good engineers, and this is what I mean by engineering is doing this stuff. We have quantified objectives, quantified costs, and we quantify the goodness of the architecture. So this is what I call engineering. And it's called logic, because we can now use logic based on the numbers in the engineering. And I think it should be mandatory in absolutely all enterprise architecture to use something like these tables. If you have a better alternative, go ahead and tell me about it. And there are things like quality function deployment and balanced scorecard that are roughly in the same territory, but I don't think they're as good. But there are other, but we need some kind of tables with numbers to evaluate the multiplicity of effects of our architecture before we invest in them beyond the point of no turn back. And we can see potentially bad things at early stages before we've made a final choice. And then introduce the idea of architecture efficiency, which has a very large number of consequences. We can talk about the profitability of the architecture, how good the architecture is, the skill of the architect. We can compare different architects. We can prioritize and decide which ones to do first because we're agile, and a whole lot of other things. And here's just our general picture of it. And then finally, here was a simple table done for planning the COVID crisis. Wouldn't it be nice if we were invited to really help them plan the COVID crisis in Norway? They're doing a pretty good job. I'm not sure I would disturb them because they're good scientists and they're listening to the science. And actually, that's good enough. My complaint here is that enterprise architecture, as we know it, isn't looking at the science and it, in other words, facts and feedback and estimates, the knowledge of what's happening in other parts of the world. So just the fact that they are essentially good scientists at the people are really running it and advising the government is the important thing, as opposed to some other governments like Brazil and USA, which weren't really very good at listening to the science and even deny the science at all times. So we see what happens with them, don't we? And finally, even fairly complex engineering efforts can be simplified to the point where the minister or top manager can easily understand why, what is the difference between the different sub-architectures and understand that they can choose any one of these safely. It'll have a lot of big effects. It'll make them look good politically at very low cost, which won't embarrass them by being delayed or costing more than the budget. So that's all I wanted to do on Thursday. We're going to go to part 3, then constraints in more detail. But my alarm has rung. I'll put this picture there, and we'll go over to questions for up to a half an hour. And I also remind you that if you think of a question afterwards or a request for more information, if you email me at tom@guild.com, which is in my picture here, I'm very happy to, on the first lecture, I managed to answer everybody same evening. Some of you will know. And love to answer your questions and keep the conversation private, suggest additional reading materials, though I think you have more than enough studying the C book as it is. Okay, with that, I hereby open for questions, and I'll take a look at everybody's picture here. Who would like to ask the first question?
Could I, please?
Kjell Elvis, how do you do?
It's just it's a wrong name. My name's Tom. Sorry about that.
Okay.
Yeah.
what is your real name?
Tommy Freeberg.
Okay, Tommy.
Yeah.
I'm Tommy too. Go ahead.
Yeah.
It sounds like you're in Norway somewhere.
Yeah, that's right.
Okay. Go ahead.
But I'll do it in English. I'm looking at page 17 and the poverty and hunger and those goals.
Yes.
And I was just wondering, there you have like from 0 to 100. But
yes,
are they weighted compared to each other? So yeah.
Got your question.
Yeah.
So now I did not explain. I explained a little bit of what this means, right? 95% means 95% of the way to the goal. But I did say we're going to look more deeply into this method in various times. So there's a lot to explain about this. I mean, I could spend easily 4 hours just explaining the table, and clearly I didn't have it now. So, okay, so there are lots of things that are not yet explained, so it's quite fair to ask a question and I can give at least simple answers. Now, so the meaning of this percentage number is 0 means no contribution to this goal, meaning that if we implemented this architecture, we would be where we are, which happens to be the status number, okay? So 0 means we're not moving ahead, but it also means we're not moving backward. A minus negative number means we're actually worse than we were before we implemented the architecture. Okay, so that's the slightly better explanation of what the percentage means. But your question was about weights, okay? Weighting. So let me give you the short thing on that. Now, number one, we're going to talk about prioritization. Let's go back here. You see, it says chapter 5, prioritization. Okay. Yeah. So that is next Thursday. I hope I guessed rightly. So the long, and that means you can read ahead details of my answer in chapter 5. That's number one. And you will get references to some even more detailed writings I've done, like a 60-page chapter on prioritization from my value planning book. I'm quite sure I've given you a free copy of that you can have right now. But I'll give you the gist of it. Many methods, for example, the balanced scorecard and quality function deployment I've mentioned, they have built into them a weight. You mentioned the word weight, right? Yeah. Like a weight from 0, meaning no weight, to 5, or 1 to 5 stars. And you all know these kinds of weighting systems. Now, in the old days, when I was using, old days meaning 50 years ago, when I was using early versions of this method, which I called MECA, multi-element component comparison and analysis. How's that? And I had weights. I weighted the different values, okay? Yeah. So, and that's pretty much what quality function deployment does. It puts weights on it. Now, I'll make a long story short. I learned something. If I am able to quantify the values, as opposed to just say good security, but I'm able to say I want 95% probability of capturing a hacker within 5 seconds.
Yeah.
That's quantify. If I'm able to quantify, then I don't need the fixed weight numbers. I don't need them. Not only don't need them, I don't want them because they're fixed. Why? It turns out that the moment you go to numerics for these things, that numeric number helps you do prioritization. It's just a tool to help you prioritize. But it's the prioritization you actually want, okay? And we don't want fixed prioritization. We want dynamic prioritization. Let me give an example. Do I want to, if I'm trying to survive and I need air, water, or food, right? I don't want to fix the priority on, say, air, because after I do that, I will always prioritize air, but I will never drink or eat, and I'll starve to death or dehydrate to death. Okay, so fixed prioritization is actually a danger in a dynamic environment where things like the supply of resources changes or the degree of values change. So what we do, making a long story short, again, reading your chapter 5 will give you a lot of information about it. We use the numbers, which we've now always have obtained, in the values, and we use what we actually use is the distance. When we deliver something in a sprint and we measure how far we got, as we close the gap, we deliver the value of security. And we've reached our security level. At that moment, security has no priority because it's satisfied. But if user friendliness has a big gap between what we can measure we have and a requirement, then it has, per definition, until further notice, a higher priority than security, which has already been delivered. With air, water, human body, if you like, our prioritization system granted by nature and God is dynamic, and it's based on how much water you need and food you need and air you need for survival and for comfort, okay? So I believe in God's, I say it very dramatically, God's own prioritization method. And just like it was said that Einstein believed that God did not use dice or didn't do random choices, I believe that God doesn't do fixed weights. God or nature, take your choice, has understood that dynamic, large, complex systems need dynamic prioritization. And that means we need to recompute our priorities after every agile delivery step and use that information to decide which values need satisfaction, like user friendliness needs it, security doesn't, and which strategies or architectural things need to be plugged in at this moment. It's a fairly long answer, but it is radically different from childish, useless for complex systems theories about prioritization called fixed weightings. Okay, you will find references to several papers on what's wrong with fixed weights in that chapter and in there. And I'm surprised more, I know that some of the architectural methods we have, they actually have fixed weights in there. And I would argue that is a not very good method for large complex systems like Axon. They are, by the way, I would say that fixed weights are okay for small and limited systems, like understanding my grade point average for getting into a university. Okay, there's nothing wrong with fixed weights for certain environments, but the environments where enterprise architectures are working, like large government projects, they are arguably a very stupid idea, and it's time, I'm calling it out. You can argue against me if you like, but read the arguments first. Common sense says that dynamically changing architectural decisions is necessary in a very complex, difficult to understand, changing world. I give you everybody's COVID crisis as a perfectly good example of the complex, changing, unpredictable worlds we have to live in right now. That, Tommy, was my answer.
Yeah, because when you say it like that, how would you compare the different goals on page 17? Is every goal set to 0 to 100% in like getting out of the red zone, if you understand what I mean?
Yeah, page
17.
20. Yeah, okay. So let's see, I need to get your question in my mind very clearly. Let me state something and ask, did I answer your question? Okay, so the project starts before anything is delivered, but after a good deal of architecture may have been performed. And the project starts at what we call the status level. So this status number is where the existing system is before you start applying any new architecture, okay?
Okay.
So, and now our priority in general is to get to what the target level, and that's this goal, whatever it is, okay? So goal is defined as success, where we want to be, and there's a date on it, when we want to be there, by the way. And they may have multiple goals for different, like for the older people above 85 years old, have a totally different goal for giving them a jab than for teenagers, right? And health workers. So we'll get into that, but we simplify here and assume there is only one goal. We need to keep on architecting and implementing an architect until this goal is reached. And if this goal is reached, but not the others, we need to keep on architecting until all goals are reached.
Okay.
When all goals are reached, we've done enough architecting and enough project management, and we're done with the project. Agile people are always arguing about the definition of done, and they think it's when they've coded all their user stories. And that's ridiculous. You are done when you've achieved the critical objectives of your critical stakeholders, no matter how many user stories you've coded or not. You can code no user stories whatsoever and achieve all of your goals, and you're done in real projects, okay? Nobody cares about the user stories except silly programmers and user story people who have corrupted Agile, if you don't mind me saying so aloud. Did you get some kind of an answer, or would you like to rephrase it?
I think so, because I only thought it was kind of hard to compare apples and oranges, if you get my meaning.
Right.
But
no, we use this table. We even have it in the competitive engineering book. We have a page about apples and oranges comparison. So the people say you cannot compare apples and oranges, and we say, yes, you can with this table. Okay?
Yeah.
So remember, the competitive engineering book is a free downloadable book. You'll find it in the references and on our website, guild.com. And let's see if I, just for fun, look in the subject index under apples and oranges. Oh dear. Not good enough index, is it? But anyway, you'll find it in the impact estimation chapter there, which is, you'll find it in the impact estimation chapter. Let's see. Well, I think it's in there. Maybe it's in another book. Okay. But long story short,
good answer, and I'm not going to steal any more time. Thank you very much.
Okay. So next question then.
Hello, Tom.
Hi, Agan. Were you from India?
Yes.
Wonderful. Welcome back. Where in India are you located?
New Delhi.
New Delhi. You said that last time. Right. Okay. Welcome. I just had yesterday I did an interview for a friend of mine, 1 hour about my life history and personal history. And if you look at my LinkedIn or Twitter, you'll get it. But I got interviewed about it. And you'll also see me in a picture in full Indian costume, where my son is doing a full Indian wedding in India.
Nice.
Yes, your question, Yaga.
My question is related to this diagram itself. when you were explaining about Agile, how would we use Agile to implement this solution? So you said that if we want, in our first iteration, want to implement poverty, then we could choose the first architecture, S1 and poverty, which is 95%. And then if we want to implement next phase, like and hunger, then we can choose this S2 and hunger. So my question is related to, aren't we choosing local optimum solution to have an, instead of having an overall optimum solution?
Sorry, I didn't get the last part of your question. It's something about a local optimum, and you lost me.
So in this respect, we are choosing the optimum architecture for poverty or hunger.
Yeah, I would avoid using the word optimum. It's a very dangerous word, but I'd simply say that if I chose S1, it is the best known architecture for if I prioritize ending poverty first. But if my management committee says, no, we want you to end hunger first, then S2 is the best architecture for doing that. So it's a matter of at a higher level, what do you prioritize of the values? And there will be people who have power to, like your steering committee or something like that, or your client, to choose arbitrarily, maybe for no good reason, but they choose. And then you choose the architecture that suits their choice of value. Okay, by the way, so this is a way of organizing. I call this agile engineering because we are using my methods to do agile here, where agile is maybe doing first step this one and second step this one, etc. These are potentially sprints. So am I answering your question?
I mean, my question was slightly different. My question was related to, we are taking the best architecture to satisfy poverty. We are taking next iteration, we are taking the next optimal architecture to satisfy hunger. But it's possible to satisfy poverty and hunger both. The optimal architecture may be a third one.
Yes. Okay, now notice something here, that our evaluation is that the end hunger strategy 2 not only largely delivers the end hunger objective, but it delivers maybe half of end poverty. So, so the moment we choose N2, we are choosing to do a little bit of this, a little bit of that at the same time. Okay, so if I said I want a little bit of each, S2 is my objective, and S1 is not my objective because I don't even know. I haven't even evaluated how much end hunger I get at all from this one. Sorry. So
haven't
yes.
we implemented end poverty already? Then we are going for the second architecture.
Your voice is trailing off there.
So Tom, we have already implemented the first S1 and poverty in the first iteration, and then we are going for the second iteration. So is this represent a rewrite of S?
Yeah, okay. So you want to assume that we've implemented S2. When we did it, the effect on poverty was unknown. Now, so anything can happen, and we can measure in principle what happened. Now, let's just say, for example, we implemented S2 and we got 100% of end poverty. That's a possibility. Then there would be no need for S1 at all. We dump it because we've already achieved G1 accidentally, and we didn't know it until we measured it. We could also say it's very dangerous to implement S2 not knowing this. So we must try to make some kind of estimate of how it will impact poverty before we choose to do it at all. It's too dangerous it's generally speaking, very dangerous to implement things with known unknowns because they could destroy the whole system. Am I helping you a little bit here?
Yes.
Feel free to write down your question by email and we'll talk a little bit about it by email. I've got a feeling like we need to clarify there. We want to have one more go.
One question that I can ask, it's for the next page, and it is
Okay.
similar, is on similar lines that when we are measuring efficiency based on these parameters, are these also weighted, or these
No.
are just the parameters?
Okay. So in my system of thought, which is called language or planning language, it's in the competitive end, it's in this book. There is no such thing as a fixed weight number that is common in other systems. I have banned it totally. After having used it for over 10 years, I realized that I do something most people don't do. I quantify all the values, all the qualities, no exceptions. Everybody else uses bullshit, nice sounding words for the most part, okay? Now, but the moment I quantify the values, I put a number on the goal for all the values, I can use that number as a device to help me prioritize. And the rule is very simple. If I have in my stream of sprints, my stream of value, if I have already achieved that numeric value, there is no priority. If I have not yet achieved it, there is some priority. And I compute priority sprint by sprint. This is very advanced Agile, to compute priority based on the degree of completion of the numeric value goal. Okay, so no fixed weights at all, because I think they are dangerous and stupid, and they are unnecessary if you quantify all the values, which most people don't do, so they need fixed weights. At the moment I had learned to quantify all the values, I realized that the fixed weight was disturbing and static and big bang thinking. And I have always been doing agile thinking since 1970, 1960 I did it, 1976 I published it in the software metrics book. So because I was always agile, and I very within 20 or 30 years, in other words, my software metrics book, quantification, was published 1976. So as soon as I had learned to quantify all qualities, then I realized that the fixed weights ideas from obsolete ways of thinking, like quality function deployment and balanced scorecard, they were, the fixed weights were not only not necessary, they were disturbing and didn't allow the architect to be dynamic and tackle a dynamic changing environment like the COVID environment, which we have to tackle. That's where we are. So it's fixed weights, obsolete. The new generation, which is this technology, this is absolutely all values and qualities always quantified. Okay.
Right.
Next question. Chetan is thinking about asking a question, but microphone isn't.
No,
There he goes.
I had a connecting question, but I thought maybe someone else wants to ask to have a chance. So
You're on.
the connecting question was,
Chetan, where are you?
I'm from India, Delhi, and Jagan has introduced me to this course, so we are
Good.
colleagues.
Where are you? Oh, you're in New Delhi area.
Yes.
Okay, welcome to Norway. Your question,
Thank
go
you.
ahead, do it, Chetan.
So my connecting question was, I do understand that weights might be disrupting, but initially, if you have to compare between different architectures, etc., weight do play an important role, and that is how you have kind of quantified in this slide. You've added kind of weights, if not weights, the percentage of achievability on different items. So somewhere, does it really play an important role when we look at it, or should we always kind of just see what is the need of the hour, or what is the management, or you say what is the decision that they want to be implemented first? That should be the governing factor.
Okay. So I haven't got a perfect question yet, and we don't have enough time to parse it perfectly, but let me try to answer a little bit, and feel free to email me and discuss it with me. Here, the moment your stakeholders have said, this is our goal, and this is our goal, and this is our goal, they have actually set some priorities. Their priority is to get to these goals in a certain time, and usually with some more detail about a certain place, like with people over 85 years old. Okay, now, okay, so we set priorities when we quantify and specify our values. So when priorities are achieved as measured by your a set of incremental deliveries, then there is no longer any priority because you have reached what has been prioritized. So there is no point where we need a fixed weight to achieve this understanding. We need a quantified value to achieve understanding of whether things are still prioritized, not achieved yet, or they're achieved and there is no priority. Now, your question about looking at the overall architecture, we do it in two ways. We look at the theoretical architecture, that is before we have implemented it is theoretical. And we use the table and our estimates to theoretically understand if this architecture is better than this architecture. And we use a rough addition of the numbers. These two numbers, 128, 140, just mean they're a hell of a lot better than zero, and they're roughly the same. So it doesn't matter what you choose. Okay, so we use a rough modeling. It's not perfect modeling because they don't really perfectly add up, but they add up well enough that I can use this number to prioritize maybe 140 before 128, and these have no priority because it's not known what they do. Then I can start looking at their costs. So now, when you start delivering increments, agile, of the values, you build up a picture of how close you are getting to your goals. And this is called feedback. And we use the degree of feedback compared to the objectives to prioritize what should we do now that we know the real situation of the first 50 sprints or the first 3 years of Axon project or something like that. Okay, you use feedback from reality to decide whether the architecture you have is sufficient or whether architectures that have not yet been deployed need to be deployed. Okay, so there are two scenarios. There's first the purely theoretical architecture in usually the first week of a project. I do this theoretical architecture, okay? And this just sets the stage for initial prioritizations. What are we gonna do in our agile sprints or delivery steps on the second week, the third week, the fourth week of the project. And then the feedback from each step where we measure what has really happened here actually gives us information that helps us prioritize which architectures to put into play, which architectures to delete because they give far less value than estimated at far greater cost, and things like that. So in other words, the architect is actively participating, as in the IBM clean room method, at each incremental step and looking at the feedback and making decisions. Shall I deploy some architecture which has not yet been deployed? Shall I modify some architecture so it's the same architecture but it's cheaper? Shall I find entirely new architecture? That's what the my dynamic architecture idea does in the new dynamic agile architecture, which I'm teaching here. So let's see, that's 1 minute before we draw a line, but would anybody like to squeeze in one more question quickly, and I'll give one more answer quickly.
Thanks, Tom. It was very. I have one question. Is the these percentages, are they percentage achievements?
Yeah. So So here, this is percentage of achievement. So 100 would be, we have achieved this goal on time. Okay, 0 would be, in this case, it's unknown, but 0, there's my alarm. 0 down here means we've estimated that this architecture does nothing to the status and we will remain at the status number.
Yeah, so like here, you have that 95% on the poverty on the first column, and you have the 96% on the second column, you know, the end hunger.
Yeah.
But it's not necessarily that 96% is better than the 95% because it's just percentage achievement.
Well, first,
one might be much more valuable.
First, this 95% applies only to the poverty goal. This 96% applies only to the end hunger goal. So they're connected, literally.
Yeah, but yeah, but 95% of the first one might be more valuable than 96% of the second one.
It might be.
Yeah.
And now, by the way, I learned something years ago when developing my methods. To get perfect modeling requires far more effort than simply implementing a sprint and measuring. Okay, so my limits of my methods are when it takes so much effort to decide and analyze which one is better. It's just cheaper. It takes 1 week to just do it and see what happens. So long story short, my modeling, my theoretical modeling has limitations. It's, in a sense, it's quick and dirty modeling so that we can quickly get into action and start delivering and measuring. Because my view of complex systems is only by measuring the real system do you have real knowledge. And that is a scientific principle. Sort of an answer.
Thanks. Yeah, thanks.
We can continue discussing, but it's a good question, but there are limits to how good my modeling is, and that's on purpose, because it's cheaper to get good answers by doing real stuff really early. That's an important point. Okay. Any other questions? Email me or save it for the next time. So we're meeting again next Thursday, and we're going to do part 3, primarily about constraints. This one got a lot of principles about constraints. You can read ahead if you like, or read it afterwards, or not at all. But I'm going to do a lot about constraints. And then Thursday next week, the decomposition. How do you decompose architecture in smart ways?
Yeah, so the
did I say Thursday?
Yes, Tuesday. Yeah, the Thursday meetup in 2 days, that's already posted on the web, and I'll publish the Tuesday meeting soon.
Right.
So
this is what we're going to discuss. These again, what I've found is that the architectural techniques that are popular, I'm talking about, TOGAF and Zachman and any of these others. If you take a deep look, they're not very good on specification of constraints and the use of constraints to evaluate architecture. It's like not there at all, or it's very weak, but it's not strong enough, in my opinion. So that's why I want to bring it constraints in a very strong way. And just for fun, the constraint that Norway was obliged to follow the European Union GDPR laws of privacy when building the Smittestopp for COVID tracing was a constraint that was clearly there if you'd asked the government lawyers, but Simula decided to, on their own, downplay that constraint as not as important as getting the tracing done. But when finally the government was asked, they had a very clear answer. That constraint is a hard constraint. We're going to dump all your work for the last few months and start again, and we're going to respect that constraint in the new COVID tracing thing. So there's a real live example of constraints not understood and respected in Norway. And probably every project, every country has problems like this that don't show up until after the system is built and deployed, which was the case with Smittestopp. Okay, that's not good enough. Now, you might say, who is responsible for this? And I'm saying the business analyst function is responsible for identifying the constraints, but the architect is responsible for evaluating all architectural ideas with regard to those constraints. That's it. Welcome back on Thursday at 4 o'clock Norwegian time.
Yeah, thanks a lot. And I think it's really good that we've got some people from India coming as well. So
yeah, welcome India.
So it's we get
Don't tell everybody in India. We wouldn't have any space for Norwegians here.
We got our Zoom licenses for 100 people, and we had about almost 50 today. So we still got space for.
Yeah, we still have practice.
If somebody wants to join,
line up and really come, but 50 is good.
Mm.
Good to know. Okay, so see you either by email this evening or tomorrow at 4, or
Thursday at 4.
Thursday at 4 tomorrow.
Yeah.
And thank you very much. And you can read ahead and read backwards until you get it.
Yeah. Thank you, Tom.
Thank you all.
Thank you.
Bye-bye.
Okay, bye.
Bye-bye.
Bye-bye.
Bye-bye. Turn off the recording.